Hello everyone, this is lecture 2 of thermodynamics in GR 130 for June 26, 2020. Today we're gonna wrap up with section 1.4, talk about section 1.6 and section 1.7 in chapter 1. Then we're gonna go ahead and start with chapter 2, which is about energy. Later after we finish this. So let's start with phases. What is phase? Phase, this is a very end of chapter section 1.4. A phase is a quantity of a matter that is homogeneous throughout the system. Say if I say the water, we have liquid water, we know the density, we know the pressure at, let's say, 25 Celsius and 1 atmosphere. If you cool it down, decrease the temperature, you're gonna have solid, we call it ice. If we heat it up, we have a gas, we call it vapor. So above 100 degree, let's say 100 Celsius and 10 at 1 atmosphere, and this is like negative 20 Celsius. So we get different phases, all of them liquid, the same chemical composition. We're gonna talk later about the pure substance, but this is a phases, different phases of this substance. Now we're gonna talk about the state. What is a state? Section 1.6. A substance with particular set of properties, we call it a state. I give you a cup of water. I told you this is water. I give you pressure, temperature, volume, mass, specific volume, anything, it's called a state. If I heat it up, go another state, maybe ice or maybe vapor, cool it down and become ice, another state. So this is called a state. We have a very important definition in a state. It's called state postulate. State. What a state postulate is, this is you. It is of a simple compressible fluid is completely specified or defined by two independent intensive capital properties. So if I give you two independent intensive properties, you can know everything about this state. Two independent intensive should be intensive, and they are not dependent on each other. For example, temperature and specific volume. They are two independent intensive property of any state. So if you give you these two, you can know everything else. You can get pressure, you can get energy, get entropy, you can get anything about this state just by knowing only two independent intensive property. We're gonna know that in more details when you go to steam table and equation of states. Let's say I give you density and specific volume. They are the same. Rho is 1 over specific volume. So I can give you two because they are dependent. They are two dependent. No, we need the independent properties. Section 1.7, we're gonna talk about equilibrium. Equilibrium means balance. Something in balance. Imbalance. When I say, for example, thermal equilibrium, it means temperature is constant, the same throughout the material or substance or system, the system. So if I give you a cup of water, it has some ice and some water. If the water, like let's say 10, and this ice is 0, this is not thermal equilibrium. But everything is 0, you can have liquid in 0 and the ice in 0. They are both in thermal equilibrium. Thermodynamics only deals with equilibrium problems, only thermal equilibrium problems. Everything need to have the same temperature throughout the system. So let's say you have a state, It's thermal equilibrium. So you have a state. Let's say state 1. It has pressure, temperature, two properties. And you go to another state, state 2. It has another pressure or temperature. Let's say plot them here. Property A and property B. They are two independent intensive properties. This state 1, this state 2. Let's say you compress the gas. So you get from low pressure to high pressure, low temperature to high temperature. This is called compression process. It can be linear, it can be straight line, it can any line, any shape. This is called process. So process, a process is system undergo from one state to another. So you have here low pressure, low temperature, compress it, became high pressure, high temperature. You can go back until this point. So if you keep doing that and you turn it back to the original position, we call this cycle. So we have cycle when a system returns to its initial state. Should be returning back to initial state. So I start at 1, go 2, go 3, go 4, go 5 to anywhere, then go back to 1. This is a cycle. If I don't go to 1, it's not a cycle. So this process 1, process 2. So equilibrium, which is one state. Process, two states. Cycle, many processes until we go back to the end of initial state. Need to go back to initial state. Some processes have constant property. We have some standard processes. We have very famous three processes. If the volume is constant, like specific volume is constant, if you have temperature is constant, pressure is constant. This process, we call it isochoric. This is called isothermal. Thermal means temperature. This is called isobaric. Sometimes we call this isometric. So we have here, all of them have the part iso. It means something similar between two states. So going from state 1 to state 2, or 3 to 4, 5 to any two states, they have the same volume. V1 equal V2. Isothermal, T1 equal T2. Isobaric, P1 equal P2 between state 1 and 2. A steady flow, no change with time. Last thing, steady flow, no change through time. There is no change through time. Now, we finished chapter 1, we're going to go chapter 2. We're going to go now to chapter 2, which will talk about energy. More details about energy. So energy, by definition, is the ability to cause a change. It's the ability to cause a change. We keep saying about the active kids, they have a lot of energy. They could do a lot of changes and broke stuff. We have a lot of forms of energy, several forms of energy. So section 2.2, the forms of energy. We have a lot of forms. For example, thermal energy, mechanical energy, kinetic energy. We have nuclear energy. We have chemical energy. We have a lot of forms of energy. Magnetic energy. Magnetic energy. We have a lot of forms of energy, forms of the energies. Let's take about some we're going to deal with during this course. Start with kinetic energy. We used to use key A like this, which is half mv square. This is kinetic energy. If we set a specific kinetic energy, we used to use K small, E small. So distinguish between the value and the specific value, we use capital, small, uppercase and lowercase case. So Ke small, it's half V square, velocity square. So the difference is we divide by mass because it's specific. When something is specific, we divide by mass. Like for example, potential energy. PE, or just P, it's mgh, or Z, if we're talking about elevation Z. A specific potential energy, we use P small, E small, just Gz, we divide by mass, give. We have internal energy. We used to use the symbol U. U is a summation of all internal energy in the system. System has a lot of internal energies. Molecular energy, you have molecular interaction, nuclear energy. It has internal work. All of these forms, all of these energies, we come up with this. So this is the sum of all internal energies. We call it U. And we don't care about the details. We can just give you a U. Think about temperature. It will be like a U. Something times temperature gives you an internal energy. Also, we have a specific internal energy, which is U small, just the uppercase U, which is internal energy, total internal energy, divided by mass. If we ignore all the rest of other energies, we call about the total energy here is U plus kinetic energy plus potential energy. So we don't have any other magnetic or electric or anything else, just U, kinetic energy, potential energy. Or E small, a specific total energy, U small, a specific kinetic energy, a specific potential energy. So this specific total, a specific energy. This is total energy. What is temperature? Temperature itself is not an energy. It's a measurement of hotness or coldness. So you can say it's a measure of hotness or coldness of a system. So this cup of water has 30 degrees Celsius. So this is a reference for us. It can have high energy or lower energy. We're going to see that later. So in order to understand what is temperature is, we're going to start with something called zero First law. Zero First law, something is so simple. Zero's law of thermodynamics. This is to understand what is temperature is. It's so simple. It's like this. We are saying we have two bodies, A and B. They are in thermal equilibrium with somebody else, C. A, thermal equilibrium with C. B, thermal equilibrium with C. So the result is A and B are in thermal equilibrium. So if A in thermal equilibrium with C, B thermal equilibrium with C, so of course A and B are in thermal equilibrium. So A has 50 degrees, C have 50 degrees, they are in thermal equilibrium. B have 50 degrees and C have 50 degrees, they are in thermal equilibrium. Of course A and B are in thermal equilibrium. So if two bodies, A and B, each of them is or are in thermal equilibrium. Thermal equilibrium means temperature is the same throughout the system, with a third body, say C. So A and B, these bodies are in thermal equilibrium. Think about A is a ball of steel at 40 degrees. B is a ball of copper at 40 degrees. Copper we use Cu. And this is water. 40, 40, 40. Put this and this, thermal equilibrium. Put this and this, thermal equilibrium. This and this, they are in thermal equilibrium. As we said, we have two schools of units. We have SI unit, we have bridge units. Let's talk about both of them for temperature. For temperature, the first thing we measure with is called Celsius. The first thing is Celsius. Celsius is a scientist. He said, I'm going to measure a temperature. If the water freezes at 1 atmosphere, we call it 0 Celsius. If the water starts to boil, so water freeze at 0 Celsius. Water boils at 100 Celsius. This is at 1 atmosphere. And he defined this scale. And everybody use it after that. Kelvin, which is the most important unit in your life, in temperature, is the absolute temperature. He said, Kelvin measurement is exactly Celsius measurement plus 273.15 if you want accuracy. This is the transformation. This is the actual absolute temperature. From nothing, it means 0 Kelvin means no motion at all, which is impossible. If you have this metal, the molecules here is still moving. We have temperature 20, it's still moving. If you call them down back, it will be moving slower. If you call them back, slower. If you're able to stop the movement of any molecule, this is called 0 Kelvin, which is impossible. There is nothing called 0 Kelvin. So if you have 0 degrees water, it means it moves. With 273, 0 plus 273, it's still moving. Everything is moving. This glass, anything is still moving at even 0 Celsius. But 0 Kelvin, no movement of molecules. British has two different units, two system of units. The first one, I'm going to use the same color here, it's called Fahrenheit. F. He said the water freezes at 32 Fahrenheit and boils 212 Fahrenheit. The same as here. The transformation from here and there, Fahrenheit, is equal to 9/5 Celsius plus, of course, 32. So if the Celsius is 0, Fahrenheit is 32. If Celsius is 100, times 9/5 plus 32 is 212. So water freezes at 32 Fahrenheit, 0 Celsius. Water boils at 212 Fahrenheit is 100 Celsius. And the last one, which is the important for British, which is Rankine, the absolute temperature in Rankine. So this means we're going to use this if you're talking about British unit. We're going to use this if we're talking about SI units, which is temperature in Rankine, for example. Let's say Rankine equal Fahrenheit plus 459.7. This is the change from Fahrenheit to Rankine. This is the absolute temperature. We're going to talk about absolute temperature also later. This is the absolute temperature this is a very important unit, Kelvin and Rankine, for the SI and British. Actually, these parts are in reading section 1, chapter 1, and we read them back now after the energy definition. We're going to use them a lot. In a very simple word, force per unit area. For example, P equal F/A. Usually, we use this in SI, in Pascal, force in Newton, and area meter square, if you're talking about an SI unit. Let's take a simple example. If you want to cut an apple and you have a knife, let's say this is a section of a knife. How do you cut it? From here or there? Sharp edge or not? Of course sharp edge. Why? Because you want to have the minimum area, apply a very small force, so you get a huge pressure. You can cut from this one, from this very bad edge, but you need huge force. So simply, it's force per area. The smaller the area, the larger pressure for the same force. We have 4 measurements for pressure. Absolute pressure, absolute pressure is a measurement from zero, from the ambient, measure from vacuum. This is pressure, measure from vacuum. Gauge pressure, we measure from 1 atmosphere. Reference datum line is 1 atmosphere. Vacuum pressure, it's a pressure measure. It's actually like P vacuum is equal P minus B atmosphere, actually minus P absolute. It's a negative of this one. Relative pressure is just delta P, which is we can ignore, just a change in pressure. So it's not exactly scaled, but this one is scaled. The first 3 are scaled. It means this is a zero pressure. It means vacuum. If you are in vacuum, there is no gas, there is no pressure. So pressure, if you are here, you have above your shoulder a column of air. This column is 101,325 Pascal, 101,322 Newton per meter square above your shoulder, from here to the end of the atmospheric level. This is called ambient pressure. So this is zero pressure. If you are in a space, there is no pressure. This is zero pressure. If you have any pressure, this is called absolute, P absolute. 1 atmosphere, 2 atmosphere. Let's say this is 1 atmosphere. So this is B atmosphere, which is 101,325 Pascal, almost 100 kilopascal, 1 atmosphere, or 0.1 megapascal. This is B ambient. From this B ambient, if you measure from here, we call it P gauge, PG. PG, if you have some device, like for example in a car tire, you already have ambient outside. And you want to make sure the pressure inside the tire larger. So we measure P gauge, pressure larger than atmosphere. So if you write here, P gauge is P ambient, absolute, minus P ambient. B vacuum actually is the opposite. B vacuum measure from here, downward. B vacuum. So P atmosphere minus B absolute. If you B absolute is 0, so I measure from here to here. This is called P vacuum, 1 atmosphere. If your pressure is here, so P ambient minus P absolute, so you have this value. If your pressure larger, so you see value, negative value. So this value would be negative if your pressure greater than P ambient. Usually we care about 2 things, absolute pressure and gauge pressure. We don't care about vacuum a lot or relative pressure. Absolute pressure, we measure from 0, from ambient. This is space, nothing, no pressure. There is no gas to compress me, there is no fluid. If I have some gas, I get a little bit pressure. We have atmosphere, like this atmosphere, we have absolute 1 atmosphere pressure. If we measure after that, it's called gauge pressure. Now we're gonna get 1 principle, Pascal principle, and 2 examples. Then we're gonna go ahead with something very important in chapter 2. What is Pascal principle is? Pascal principle is pressure applied to a confined fluid, like this fluid, increase pressure throughout by the same amount. If you apply pressure here, P1 is the same as here. These two pressures are exactly the same. However, the cross-section is different. The force is different, but the pressure are the same. So the pressure, as long as this is confined fluid, completely incompressible water here, whatever pressure add here, reflected here. And this has been used a lot of application, like for example, hydraulic jack. To lift a car with small pressure, you can lift a car with a very large pressure. Here, get there, huge force compared to the other force. So P1, equal to P2, or F1 over A1 equal F2 over A2. This is Pascal principle. Let's take two examples. Example 1 is 156 in the book, textbook, edition 8 from our reference book. We have a girl, she wants to do skating, and you give her weight, her mass, and they said the maximum pressure the ice can withstand with is 0.5 kilopascal. If it's more than that, the ice will break. And her weight, her mass was given 70 kilogram. He said, what is the maximum or the minimum area needed for this? If it's the area is too huge, it's okay. But we need the minimum area needed per shoes so she can stand up without breaking the ice. So we have here two areas, though. So we have pressure equal F over A. This is the maximum pressure, 0.5 kilopascal. It means 0.5 times 1000 Pascal. This is Newton per meter square. The force is mg. The area is actually two areas per shoes. So it's two areas. 2 times area of one shoes, which is the mass is 70 kilogram. Kilogram is fine. The same as kilogram per meter second square. G, our gravitational acceleration, let's say 9.8 or 9.81 meter per second square. So everything now is fine. This area, shoe, I don't know. It's a meter square. So all the units are fine. So the unknown here is area shoe. Area shoe, or maybe I got two area shoe in my calculation, was 0.687 meter square. You can get one shoe's area. If the area greater than that, it's okay. The pressure will be lower than 0.5. But if the area is lower than that, the pressure will be larger than 0.5 kilopascal, the ice will be broken. That's a very simple problem. Problem 51 was a manometer. Manometer is something like mercury like this, and we put a mercury tube like this. This is mercury everywhere, Hg. We know that its density 13,600 kilogram per meter cube. You know the acceleration is 9.81 kilogram meter per second square. The mercury, if you have here P 1 atmosphere, and here is 1 atmosphere, the mercury will go up here until certain height. This height is 760 millimeter. He measured that. He gave it to you. He gave you in this. He said, give me the atmospheric pressure. So the pressure here, at this level, the same as here. This is continuous mercury everywhere. So the pressure here, the same as here. Since P1 equal P2, P2 almost this only, this is negated, so it's rho GH mercury, which is 13 kilogram per meter cube times 9.8 meter per second square times 0.76 meter, which is 101,325 Pascal. This is the ambient P atmosphere. What I want. Hello, welcome back. So we're gonna continue from chapter 3 about composition or chemical composition and what is going on with heat and temperature and pressure. This is the most important chapter from now on to the end of the course. I like this part of the whole course. I like it a lot. So let's start with a very simple definition. It's pure substance. It's pure substance. It does not have any change. So we have a substance, material with fixed chemical composition. So if you have a cup of water with some glass, with some ice and water liquid, these both are pure substance. Yes, it's ice solid phase and this is liquid phase, but all of them H2O. So it means this is pure substance. If we add heat, it can be all of them go vapor, or some liquid, some vapor. So it's still pure substance. So let's go section 3.3. I'll give you a cup of ice. Let's say you have some ice, block of ice, bottle of ice. It has some volume, some mass at, let's say, negative 15 Celsius. And we're going to do a test, a very important test, which is we're going to add heat versus the temperature or temperature. Let's make temperature. Heat versus temperature. So we're going to add heat and see what happens about temperature. So initially it was minus 15 Celsius with some energy. Let's say here this is the energy. Heat is the energy. And we're going to add more heat. This one will start to melt. So it's going to get warmer. Until a certain temperature, which is 0 Celsius, definition of 0, it starts to show some liquid. So if you have a container, you see liquid start to melt. However, the temperature remains 0, but this still going melting. Oh, the energy increases. This is A, B, C. The energy increases, heat. I'm going to add heat, but the temperature does not increase. If you put a thermometer, you cannot see more than 0 Celsius at 1 atmosphere. You cannot, it's impossible to see more than 0 Celsius. Put it, let it melt, add heat, you only see 0, 0. Until complete liquid here. So here we have liquid, pure liquid. Everything is pure substance. So everything is pure substance. But here ice, complete ice, 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 ice and liquid. Liquid start to show up. Liquid and ice, liquid and ice. Here complete liquid. Then here, this liquid temperature now from here increases until 100 Celsius. Definition of Celsius. At 100 Celsius, some vapor will start to show up. Some vapor will start to show up. Everything is pure liquid, but vapor will start to show up. Temperature remain 100 Celsius at this 1 atmosphere, of course, until, let's say, C, D, E. Until certain point, everything is vapor. The temperature increases. So if you have a thermometer, you only measure 100 Celsius. No way you see 101, 101 or 99. It's impossible. If you have 1 atmosphere, you only see both of them, some vapor and some liquid. As long as the pressure is 1 atmosphere, pure substance. There is no salt, there is no sugar with the water. So AP, BC, we used to use the word fusion, changing from ice, solid to liquid. From DE, we used to use evaporation. It means changing from liquid to vapor. Vapor starts here. But here, complete vapor. Everything is vapor. Now temperature can increase. You can see 101, 102, 103, 200, 500. We're adding energy. Still adding heat. So we add heat here. We add heat. We add heat. So you see this? We call it isothermal. Temperature is the same. This is isothermal. we care a lot about this part. We're gonna draw this part, starting from liquid, vapor, vapor, continuous with vapor. This chart is so important for you in your course. Let's redraw 3.4. Something is so good, so good. We're gonna redraw between two independent intensive properties. Let's say specific volume and temperature. And I give you some liquid at 15 Celsius with some volume. Volume is about 0.001, and this is a very important number. We talk a lot about it, which is meter cube per kilogram. It's almost 1 liter of water for 1 kilogram, 0.001 meter cube per kilogram. It's almost 1 liter. If you heat it up, the volume almost does not change. It's like very small change. Until at certain temperature, let's say 100 Celsius, this is 1 atmosphere. Now it starts to melt. The volume increases while the temperature the same. At a certain specific volume, almost 1.67 meter cube per kilogram, almost 1 cube. So it started from this almost 1 liter, which is 0.001 meter cube per kilogram, until 1.67 kilo, almost 2 meter cube per kilogram, more than 1,000 times the volume, but the same kilogram, 1 kilogram. Then now you see increase in temperature. So here is isothermal. Everything here is 1 atmosphere. Okay, so I have a cup of water. It was water. When I get heat, suddenly it expands, it became vapor. Vapor is much bigger in the volume. The mass is the same, but much bigger, more than 1,000 times. Occupy much more space. The pressure is the same. So this is like free piston, like this, until I keep the pressure the same. So it expand. So keeping expanding, and getting 1,000 times more this. Then the temperature increases. If you put here a thermostat, you only measure 100 Celsius in this part. So the pressure is 1 atmosphere, and the temperature is the same. Let's say I'm gonna do something. I'm gonna do adjustment here. Let's say I'm gonna put the pressure here lower. Pressure lower. Let's say half atmosphere. This is, I will fix it so it will be lower pressure inside. Always the pressure inside, let's say 0.5 atmosphere. So what happened with this color? What happened with 0.5? So I started here. I'm gonna add. So it is gonna start evaporate faster. This is 0.5. Because I did not apply much pressure, the water starts to evaporate lower than 100. It can be like 70 or 80 or 60 degrees. It can start to evaporate. How about if I make it 2 atmosphere? So 15 degrees, it's gonna jump to here, for example. Let's say, if you have another color. So let's say here, we're gonna add pressure, energy. Something like this. This is 2 atmosphere. This is 1.5 atmosphere. This is 1 atmosphere. At different pressure, constant pressure. This is constant pressure line. The pressure is constant, 0.5 atmosphere, which is about 50 kilopascal. This is almost 100 kilopascal. This is 200 kilopascal, and so on. If we keep doing that, we're gonna reach something very interesting, which is called steam table, something like this. If you keep doing that, this line is called saturated liquid. Everything here is pure liquid. Saturated liquid. Everything here along this line, saturated vapor, completely vapor. Beyond this point, superheated vapor. Everything is vapor, pure vapor. Here is mixture. Saturated mixture, water and liquid, some liquid vapor and liquid and vapor. Here is complete liquid. Here بنسميها sub-cold. Everything here is water. Saturated, look, it started to be vapor. After you go inside, vapor and liquid, vapor and liquid, vapor and liquid, until it became completely vapor. Then it started to evaporate. And we connect this line, this is called steam table or steam chart. We have data for that. Data for 0.5 atmosphere, 1 atmosphere, 2 atmosphere, constant pressure line. You can remember that if you have higher pressure, it means you need more energy to escape, to become vapor. That's why it go up. It needs more temperature to evaporate, more energy to evaporate. But if you have a very small pressure, you don't need too much energy to start to evaporate. Let's say we plot this, for example, as PV. Let's say PV, pressure with specific volume. So we have the TV diagram. We have sub-cooled liquid here, so the mixture here, superheated vapor here. We said if we follow 1 atmosphere, it will go like this. This is constant pressure line. It's impossible to have more than 100 Celsius or lower. Always here, mixture. Some liquid, some vapor, some liquid, some vapor, until complete vapor, saturated vapor line. This point, we call it critical point. So we have sub-liquid, compressed liquid, mixture, superheated, 3 regions. We have 2 lines, saturated liquid, saturated vapor, and 1 point, critical point. 3 regions, 2 lines, and 1 point. This is all the data here. This is the constant pressure line. We can replot it with any other 2 independent intensive properties. 2 independent intensive properties, any 2. For example, pressure and volume. Let's take one line here. From here, sub-cooled, which is compressed liquid, mixture, vapor. The curve here is a little bit different. We're gonna follow 100 Celsius, the constant temperature line. It looks like this. I'm gonna describe it why right now. This is 100 Celsius constant temperature line. This is pressure volume curve. Pressure specific volume curve. This is temperature specific volume curve in chapter 3. What happened here? We are in liquid. At high pressure, let's say 202 atmosphere. This point, exactly this point, which is 2 atmosphere and liquid. Yes, 2 atmosphere and liquid. When you have this temperature and you're going lower pressure until, for example, 1 atmosphere, this is exactly 1 atmosphere. You became this point. This is 1 atmosphere with 100 Celsius. So the pressure kept decreasing until I became here. This pressure decreasing until it became here. This is 1 atmosphere. 1 atmosphere, 100 Celsius. 1 atmosphere, 100 Celsius. This is constant temperature line. When I come to this point, this is constant temperature line. I want to go here to this point. This line is 0.5 atmosphere. So the temperature will decrease. So until, for example, I came here, 0.5 atmosphere. This is exactly this point. This one here, exactly this point here. So let's say A, B, C, D. It's A, B, C, D. So this point, the same as this point. This is constant temperature line, 100 Celsius, because it's perpendicular to temperature. Everything here, 100 Celsius, 100 Celsius, 100 Celsius, 100 Celsius. I took it, wrote here, it became here, 100 Celsius, 100 Celsius. The first point, which when I would do this solid circle, this point. This one is the same as this one. When I move with 100 Celsius, I became here, this X here. I move, became this square, this is square here. So I'm decreasing the pressure, constant pressure, decreasing the pressure, decreasing the pressure, constant pressure, decreasing the pressure. If you keep doing that for different temperatures, let's say you want another temperature, lower temperature, something like this. If you connect the lines here, you're gonna get the same curve. This is another temperature, let's say 50 Celsius. If you want here, 200 Celsius. Okay, so you have here set compressed liquid in this region, mixture, superheated vapor. We have three regions, two lines, saturated liquid, saturated vapor. We have 1 point, critical point. So we have three regions, two lines, 1 point. Three region, compressed liquid, saturated mixture, and superheated vapor. And we have 1 point. Two lines, saturated liquid, saturated vapor. See you in next lecture.